different components and allows you to see if there are hotspots within the clusters and which one is the efficiency of the cooling equipment. Next slide, please. And by using this data-driven approach, recently, in collaboration with Cineca, this is work that has been done by Francesco Beneventi, my team, together with Cineca, they have used a live model, a real-time model of the cooling equipment efficiency to guide the operators, which were tuning the optimization point in the facility management of the Casalecchio system in Cineca, on the Marconi 100 system, and to tune it toward always using the maximum efficiency point of the different cooling equipments. And by applying that, we were capable of reducing the PUE of the 8%. And this can be seen in the bottom part of the plot, in the bottom right part. So actually, visualization is not just for visualization, but it can be used with a good preprocessing, can guide operators to do to more efficiently automate the execution of the data center. Next slide, please. And of course, once we have this monitoring system in place, we can also try to apply artificial intelligence optimization, so deep learning models, and try to push the bar a little bit further. So we've been researching a lot on how to use this knowledge extracted from data with artificial intelligence algorithm, deep learning models, specifically for anomaly detection and anticipation. And today we have models which are capable of predictive failures within several hours before they happens in the system by training models and applying them. And the challenge so far is also we are in the point of also putting this model in productions. Next slide, please. A piece of work that I've been doing and which we are happy to share is that recently we collected all the lifelong monitoring of the Marconi 100 system, and we released publicly available to the wide public the entire dataset, which can foster researcher for promoting and developing our solution, which uses AI at the base for optimizing data center evolutions. Next slide, please. So this dataset is composed of all the different metrics that we have been collecting, moving from holistically, so from compute unit equipment down to the jobs which are executed, the cooling, power spent in the cooling in the different IT. So there is really everything there. And we also created some additional dataset which already put some pre-processed values, such as for power. And because the dataset is pretty large, it's 31 months of data, it's a 50 terabyte of data uncompressed. So it's a lot of fun for people who want to train models. So next slide, please. So the models that we have been doing so far are models which started from anomaly detection. And in that sense, semi-supervised and supervised model can be applied, which allows you to detect anomalies which are unspotted by the operators. And within years, we moved from semi-supervised approach to completely supervised approach with the RUAD technology. And now we are also moving to use graph for modeling also interaction with multiple nodes. And this allows to have anomaly anticipation. So we can also anticipate anomalies before this really happens. Next slide, please. And these are other models that we also are been building for looking at the room, so to predict thermal hazards. So when due to global warming and to the climate, to the climate challenges that we are seeing, is that we are seeing that in the different cities during summertime we have heat waves that are always more severe than in the past, and sometimes this causes trouble to the cooling system. And so by doing that, we are capable of having models which can detect a thermal hazard, so an anomaly in the cooling system occurring hours before it is really happening. So giving time to operator to reduce the power consumption of the system to counteract this error and don't lose any computation and to not be forced to switch off the machine. Next slide, please. So finally, for optimization, we do have other technologies that are used and have been researched about creating predictive model for the power consumption of jobs. So one of the problems for doing proactive optimization of the power consumption of the entire data center is the fact that before executing a job, we don't know how much it's going to consume. So if we don't know it, we don't know how many jobs we can actually take to fulfill a power budget. And in that sense, we are obliged to reduce the performance of each of different processor entities of the job, and we don't know the implication that may have in the computation. And today, since the accounting still is based on computing hours, if you decrease the frequency of a user, you will actually make it pay more core hours. So for that problems, solutions that may work are more solutions which does an admittance check on jobs before making them executing, to making sure that you can have a subset of jobs that are executing but will run at the maximum speed. And for doing that, you need to, before they are running, to estimate how much power is going to consume. And we have been working with several models. So the most successful one was the usage of regression trees, as well as random forest with also, we are also moving to language models for processing the job scripts. And these are capable of, with high accuracy, to estimate the power consumption of a job before its execution. So that's it all, I think.